Okay, so you've learned through your homework a lot regarding derivative rules. So in chapter 3, we derived some general rules to help us find derivatives, and we can find now derivatives of polynomials, derivatives of sums of functions, of differences of functions, derivatives of products of functions, derivatives of quotients of functions, derivatives of trigonometric functions. So basically now we're able to find derivatives of a wider variety of functions, and we're using these rules that we derived. So we're basically based on the definition of the derivative, which is a limit definition. We derive these rules, and we can now use them in chapter 3. But one thing we need to talk about is, what if we had the composition of two functions? How would we find the derivative of the composition of two functions? And that's what section 3.4, which is the chain rule, is about. So what I want to do is go into the ebook. I want to go into the ebook here. And I want to just point out an example in section 1.3. So you already did a small assignment in section 1.3 where you added and subtracted and multiplied and divided functions. Okay, you already did that. Now I want to look at an example with position of functions. It should be review for you, but it doesn't hurt to remind you. Okay, so in section 1.3 in your ebook, two functions f and g, if you have two functions f and g, the composition, hold on here, one moment. One moment. I want to get to, here we are. Okay, so given two functions, f and g, the composite function, f circle g, or, well, we call it f, the composition of f and g, that's what that circle means, is defined by f of g of x, f of g of x. How many recall this composition, learning about it maybe in pre-calculus or in algebra 2? How many have seen this definition before? Okay, Nicholas has, and John, good, and Kelvin, and Anna, and Layla, excellent, excellent. So everybody should have seen it at one point or another. If you haven't, Rodrigo has. If you haven't, well, you're seeing it now. So the composing functions, I think it's easiest just to look at an example. So example 6 says, suppose you have a function f of x equals x squared and g of x equals x minus 3. You have these two functions, and you want the compositions f, the composition of f and g, and the composition of g and f. Okay, this is example 6 from section 1.3. Okay, so I guess we would call the first f with the circle g would be, well, I want to be a little bit careful here. Yeah, I mean, we have f composition g and g composition f. That's what we're finding. And so what they're doing here in the solution for example 6 is f composition g is just f of g of x. So in the f function where you see the x, they're substituting in an x minus 3 for x. And so you get x minus 3 quantity squared. That's f composition g. On the other hand, in example 6, G composition F would be G of f of x. So f of x is defined as x squared. So G composition F would be G of x squared, which is then x squared minus 3, because you substitute the x squared in for the x squared for G of x. Okay, so they have a nice example of that. And then example 7, they also have another example. Is there any question on example 6? Or are there any questions on example 6? All right, very good. Well, then let us proceed on to example 7 here. So here, they have a function equals the square root of x, f of x equals, this is example 7, f of x equals square root of x, and g of x equals square root of 2 minus x. Find each function and its domain. So I don't want to do all of these, but like for instance, part A is f composition g. So in the solution, f composition g is just f of g of x. So then g of x equals the square root of 2 minus x, and you substitute that in for the x value for the f function. And so you get the square root of the square root of 2 minus x, which is incidentally the fourth root of 2 minus x. And then the domain of that would be from negative infinity to 2, because you can't have an even root of a negative number. On the other hand, if you do G composition F, you're going to get there the square root of 2 minus the square root of x. And then they go into finding the domain for that. So really the composition of two functions f and g is the reason I wanted to just go over this briefly is because it's going to be used in section 3.4, which we're learning today, the chain rule. Are there any questions before we move on? All right. Well, let me now go into section 3.4, and of course we're going to do some examples, of course, but I want to just give you a little orientation to the chain rule. It is one of probably the most important. Well, all the derivative rules are important, but the chain rule allows you to take derivatives of a lot of different kinds of functions. Okay, so they start off here. Okay, and I'm assuming everybody can see the screen fine. They start off here by asking, suppose you're asked to differentiate the function capital F of x equals the square root of x squared minus 1. Okay, capital F of x equals the square root of x squared minus 1. Up to now, you would not be able to differentiate that. You can differentiate the x squared plus 1, because that's a polynomial, but the square root of x squared plus 1, that you cannot differentiate until today, because you're going to learn the chain rule. So they talk about how you could recognize if we can treat this capital F function, which is equals the square root of x squared plus 1, we can treat it as a composition of two functions. So, for instance, if we let y equal little f of u, and that equals the square root of u, and we let u equal little g of x, which is x squared plus 1, then the capital F of x function could be thought of as f of g of x, which is the composition of f and g. Okay, so let me just hold on here. Let me see here. I'm just thinking. Yeah, yeah. So if we treat these more complex functions like big F of x equals the square root of x squared plus 1, if we look at them as compositions of functions, in this case, this would be the composition of the x squared of the square root function and the x squared plus 1 function, basically an outer function, which is the square root function, and an inner function, which is x squared plus 1. We can and then if we found a rule for taking the derivative of a composition, we would be okay. Let me just show you. Maybe this would be a good time to use the whiteboard just for a minute to show you what. Sometimes the terminology can be a little. It can be a little bit. Well, I want to be careful. Terminology is important, but we don't need to overuse it. You know what I mean? All right. So this is your function here, your big F of x function, big F of x. And if we were to define, if we were to define trying to be very careful with the mouse. If we were to define little f of x equals the square root of x, and little g of x equals x squared plus 1, then f composition g of x would be that's by definition of composition f composition g. That's f of g of x. But what is g of x? That's x squared plus 1. But then what is f of x squared plus 1? Well, that's going to be the square root of x squared plus 1. And that was our big f of x function. Are there any questions so far? How many are feeling good? All right, Layla's feeling good. Betsua, good. Nicholas, all right, good. Well, this means then that finding the derivative of this big F function is equivalent to finding the derivative of the composition of F composition G. Okay. That's what that is. So we can look, if we treat these complicated functions as compositions of easier functions, and then assuming, I mean, we're wondering, okay, well, the next step is, what would this be equal to? We need a formula. We need a formula here. But if we can find that formula for the derivative, need is 2e's, we need a formula. If we can find the derivative for f composition g, then that would allow us to find the derivative of this big f of x function. So that's, without getting too much into the terminology, that's what we're trying to do. Okay. Are there any questions so far? All right. Okay. Well, if we're good, then I'll go back to the book, because I want to show you this formula, this chain rule formula. All right. So we'll do that. We'll go back to the book here. Okay, so how are we going to find this? Well, they talk about like suppose that, like, you see here, this dy dx equals dy du times du dx. All right, they say basically that, y, let's treat y as a function of x, or y ultimately is a function of x. But we could also look at y as a function of u, and we could look at u as a function of x. So if we regard du dx as the rate of change of u with respect to x, I'm looking at this paragraph now, and I'd make the paragraph bigger. I would highlight it if I could, but it's okay. I mean, I think you got the paragraph right in front of you there. I'm looking at this paragraph. If we regard du dx as the rate of change, well, we regard du dx as the rate of change of u with respect to x. And then we would regard dy du as the rate of change of y with respect to u. And finally, dy dx is the rate of change of y with respect to x. Okay, these derivatives are clear what those rates mean. Then let's suppose u changes twice as fast as x. If u changed twice as fast as x, and then y changed 3 times as fast as u, so u changes twice as fast as x, and y changes 3 times as fast as u, it would seem reasonable then that y would change 6 times as fast as x. In other words, 3 times 2. Because u changes twice as fast as x, and y changes 3 times as fast as u, therefore y would change 6 times as fast as x. We would expect that because we take the rate of y with respect to u and multiply it by the rate of u with respect to x. 3 times 2 is 6. And so dy dx can be treated as dy du times du dx. Okay, dy du can be treated as dy du times du dx. Now let me go back to the blackboard here and write that down. Okay, so This is the chain rule. Chain rule. So dy dx dy dx is equal to dy du times du dx. And we'll note here that dy dx, of course, dy dx is a rate, okay, as is dy du and du dx. They're all rates. And rates we can treat as fractions. So the math that goes with fractions would go with this chain rule. And what simplification happens here on the right? What cancels out? I don't like to use the word cancel. What simplifies out on the right side of the chain rule? The du. Very good. So if we were to simplify, very good, Zoe, very good, everybody. The du's simplify out, and so the left side dy dx equals the right side dy dx. Very good, Trevor. And so this makes some sense. The chain rule makes some sense. Okay, very good, everybody. Very good. So if you ever need to sort of confirm that you're doing the chain rule correctly, this is a nice way. This is a nice way to confirm it. This is a nice way to confirm it. But this Leibniz rule, this is Leibniz notation, and it's good. It's nice. But there's also something called Newton's notation, and you've seen derivatives written in terms of Leibniz notation and Newton's notation. And so what I'd like to do is show both of those to you. So are we reasonably comfortable with this little formula here? And obviously by doing some examples, you'll be able to feel feel good with the formula. But I'm just trying to kind of give you a little intuition here. All right. All right. Well, let us move ahead then. Okay, let me bring up. Okay, so let me give you a moment to copy this down. One moment. Okay, so this is the Leibniz notation. And that's good. But if we were to let our function y, define it to be f of u, and then define our function u to be g of x, I mean, it makes sense. It makes sense because based on the derivatives, the dy du, you're treating y as a function of u, right? Because you're finding the derivative of y with respect to u. So let's say y is a function f of u. And du dx, in the chain rule, you're treating u as a function of x. So let's let u equal g of x. Well, then y would have to be f composition g of x. That's how y would be defined. Because g of x, right? G of x is equal to u, right? And y equals f of u, so, y equals f of g of x. So what I want to do is I want to rewrite here this chain rule in terms of this new notation. Okay, in terms of the new notation. And so what I'm going to do is I'm going to replace the y, dy dx. I'm gonna replace the y here with f of g of x. So the left side of the chain rule is the derivative of f of g of x with respect to x. Get the parenthesis here. And then on the right side, okay, I have, again, there's the y, dy du, and y is f of g of x. But remember, we're doing du in the denominator. Du in the denominator. Okay, so u was g of x. So we got the derivative of f of g of x with respect to g of x for that portion of the chain rule. And then finally, for du dx, well, u is, of course, g of x. And so you get d of g of x dx. And so you can rewrite the chain rule here using Newton's notation. So on the left we have the derivative of the composition of f on the left we have the derivative of f composition g. That's going to equal f prime of g of x. That's what we have, here. This whole thing here is f prime of g of x. And then we have g prime of x. Okay, and so this is the Newton's notation for the chain rule. That's the Newton's notation. How many maybe like Newton's notation? How many think Newton's notation is nice? Okay, Nicholas likes it. Kelvin, okay, John and Zoe, quite a few of you. And actually, Anna, I think you'll find it is, I mean, sometimes one notation, yeah, Ian's right. Newton's is, oh, he likes Newton's better than Leibniz, okay. So, you can use either notation, but I think you'll find that the Newton's notation, I mean, each notation has its advantages, and sometimes when you look at a problem, it's easier to look at it in terms of Leibniz notation than Newton's notation. Other times it's easier to look at Newton's notation over Leibniz notation. So are there any questions on that? before we move to a few examples. Are there any questions? Okay, well, let's go ahead then and get to an example here. Okay, let me give you a moment to copy this example down. Okay, so we're looking at this problem here. Whoops, hold on. Okay, so h of x is equal to 1 over the cube root of x squared plus x plus 1. We want to find h prime of x. We want to find the derivative of this function. So the only way to find the derivative of this function is to use, well, we're going to use several things, but the chain rule is going to be involved. What other rule might we need to use in addition to the chain rule? Well, the power rule and quotient rule are going to come into play. Very good, very good, very good. And there are two ways to do this. So I'm going to show you method one. Okay, method one is to use the quotient rule and the chain rule. And it's going to go without saying that you're going to be using the power rule. And what I've done is I have a note here. Okay, I've written down the chain rule right here, that the derivative of f composition g is and I need another parentheses here. That's going to be f prime of g of x times g prime of x. Okay, so that's the chain rule. And really on the left side, when they say we're finding the derivative of the composition, that just means the derivative of f of g of x. That's what that means. So first thing I'm going to do is I'm going to apply, well, in the first step here, what rule did I apply in this first step here? And you know, these are primes, these are derivatives, right? What rule does that? Yeah, that's the quotient rule, absolutely. Okay, so now this is how I'm showing my work. This is how I'm showing my work. In your next exam, you know, I'm going to want you to show your work. I don't want to see just an answer to a problem. I want to see you applying the rules, your derivative rules. Okay. A few of you on the exam miss credit on some problems, because you might have had the right answer, but you didn't show the work. Okay, and I don't want that to happen. All right, so, all right, so All right, so what we're doing here, of course, is the quotient rule. So this is f prime times g minus f times g prime over g squared. Okay. Now, what's the derivative of a constant? What's the derivative of 1 going to be with respect to 0? Good. And very good, everybody. And for the g prime, okay, for finding the derivative of the cube root of x squared plus x plus 1, what rule are we going to have to use? Besides, I know the power rule is going to get involved, but what other rule are we going to definitely have to use? I look at the cube root of x squared plus x plus 1, and I think of it as a blank of two functions. It is a blank of two functions. What's the word I'm looking for? Well, not a product. The cube root of x squared plus x plus 1. Good try, Nick. Good try. I appreciate all participation. It's a composition. That's right, Sebastian. It's a composition of two functions. So what are those functions? Okay, so now I want to, that's right, Rodrigo, that's right, composition. And so what I want to do here is, okay, my focus now is, I know the derivative of 1 is 0, so that's good, and I'm good with everything, but now I have to find the derivative of the cube root of x squared plus x plus 1. And of course, I'm going to write that as the cube of x squared. I'm going to write that as x squared plus x plus 1 raised to the third power. So I can apply the power rule. But there are two functions here, an inner function and an outer function. So I think of this now. Now I want to mention, now I'm going to write this as f of g of x, but the f and g functions are not, they're not like the same, of course, as what I used here. So maybe I'll do a little erase here. Okay, a little erase. And now, starting fresh, here's my x squared plus x plus 1 raised to the third power. I want to take the derivative of that. So that's the derivative of f of g of x where my outer function is the cube root function. The outer function is x to the third. The inner function is what's on the inside here, x squared plus x plus 1. So if you're asked to find, if you define your f of x as x to the third power, and you define your g of x as x squared plus x plus 1, then the function x squared plus x plus 1 raised to the third power is f of g of x. And that's what you're finding the derivative of. So when you start using the chain rule, you always have to identify what your inner function is and what your outer function is. Your inner and outer. And now we'll apply the chain rule. We'll apply it. So okay, so this here, what is this that the 1/3 times x squared plus x, sorry, the 1/3 times x squared plus x plus 1 raised to the 1/3 minus 1 power. What part of the chain rule is that? There are two links to it. You know, there are two links. This would be f prime, good, of, okay, good participation, f prime of g of x. That's that part of the chain rule. Times 2x plus 1. 2x plus 1 would be, what would 2x plus 1 be? G prime of x, good. And you've done your chain rule. That's, mark this moment in your life, first time you've done the chain rule. But are there any questions? I mean, are there any questions so far? All right. Well, in the numerator or the denominator, I'm taking x squared plus x plus 1 to the 3rd power and squaring it. So I'm raising it to the 2nd power. So the power becomes 2/3. And then we can do a little bit of, you know, we can write this a little bit more neatly. We can write our h prime of x, right? That's what this is. It's the, so see, this would be very hard using the definition of the limit for a derivative. That would be like really hard to get that answer. Okay. So this is your, this is, you know, so far our answer. And we can combine, well, we have a base to the -2/3 power on the numerator. The base is x squared plus x plus 1. And then we have the same base on the bottom, x squared plus x plus 1 raised to the 2/3 power. So what can we do with those exponents? Well, yeah, so Nicholas, you're saying it could be the power, it's the power 4/3 with the 4 and subtract the exponents. That's right, Sebastian. So the way I did it, I'll go to the next slide if that's all right. I subtracted the exponents. And so let's see, how is the, not over the denominator? One moment. Let me go back. Ian had a question here. Oh, well, I could put that there. It means the same thing, but that's right. But sure, okay, no problem. Okay, very good, Ian, very good. And so I chose to subtract the exponents and write this as h prime of x, the derivative, as -1/3 times 2x plus 1 times x squared plus 1. Sorry, the derivative equals -1/3 times 2x plus 1 times x squared plus x plus 1 raised to the -4/3 power. And that's, you know, that's the answer. But you could have just as easily written it as -1/3 times 2x plus 1 over x squared plus x plus 1 in the denominator raised to the positive 4/3. That would be okay too. I tend to like having positive exponents, but you know, WebAssign would accept either. Okay. Are there any questions on this? All right, well, let me show you another method. You could use, I mean, we use the power rule also. But let's say I didn't want to use the quotient rule. Okay, sometimes I try to avoid using the quotient rule because quotient rule is harder. I mean, it isn't like hard, but you know, look what we can do here. We can rewrite the h of x as x squared plus x plus 1 to the negative 1/3 power. See that? We could write h of x as x squared plus x plus 1 to the negative 1/3 power. And then I don't need to use the quotient rule. How many kind of like that? How many think that's kind of cool? Yeah, you know, on your next exam, you know, you have 2 tries to get the answer right, and you know, you want to make it as easy as you can. Okay. All right. So here, the inner function is going to be x squared plus x plus 1. The outer function is going to be x to the negative 1/3. We need to identify the inner and outer function so that we can apply the chain rule properly. So then h prime of x would then be, so what you have here, right, is f of g of x. H of x is equal to f of g of x, where f of x is x to the negative 1/3, and g of x is x squared plus x plus 1. So now we apply the chain rule. As you see. And we get our answer quite quickly using this approach. Are there any questions at all? All right, well then let's go ahead. If there are no questions, let's move to the next example. Zoe, you cannot get rid of the negative 1/3. Nope. That is, that's there. All right. Are there any other good questions? All right. All right, well, let's move to another example. So I'm trying to give you a variety of examples, get to see maybe some different notation. Take a moment and copy this example down. Okay, so here we want to differentiate this function with respect to t, and that would make sense. And we have to be careful, to always respect our variables. So as I think of these things, I just, like on the exam, a few people missed a little bit on a problem because they would take the limit of a function with respect to t, but then their answer they would turn the function with respect to t into a function with respect to x, and of course you can't do that because it's a function with respect to t. So you have to be a little bit careful here. Everything's going to be with respect to t. So all right, what's the outer function here for this problem? What's the outer function? Good, the ninth power, x to the ninth power. And so what would the inner function be? That's right, Ian. That fraction, t minus 2 over 2t plus 1. Now, does the outer function in the chain rule correspond to, does it correspond to f or does it correspond to g? Good. The outer function corresponds to f. That's right, Nicholas. And the inner function corresponds to g. Okay, so here we go. So what I'm doing here is I'm using Leibniz notation, okay, as opposed to like the prime notation. I'm just using Leibniz notation. And of course, well, are there any questions on the first step there? So I'm going to try to, just kind of get the answer. Let me let you copy and let me know if you have any questions. Okay, so of course then, I mean, I assume everything's sort of going okay, and here I use the quotient rule. I just applied the quotient rule, and this is the kind of work I would want to see on your next exam for these kind of problems. As I said, I don't want to see just an answer. And naturally, we want to try to simplify this a little bit. We don't want to leave our answer this way. Let's simplify it. Nice things happen when we simplify. The two t's cancel out. And this is going to be your final answer for your derivative. Final answer will be 45 times t minus 2 to the 8th power over 2t plus 1 quantity to the 10th power. How many would like to do this problem using the definition of a derivative, the limit definition? How many would like to try that? Okay, I'm seeing. I got a quick no there from Nicholas. Yeah, I agree, Nick. I agree. Well, and that's why mathematicians came up with these derivative rules. But keep in mind now, for your, I'll just mention this, for your next exam, your next exam is going to cover some of section 2.7, like some of chapter 2, I should say. So like section 2.7 dealt with the derivative as a function, and all those section 2.7 problems, you had to use the definition of a derivative to find those limits. And so that's what would be expected on an exam. I would not want you to use derivative rules for problems where like sections in the book that came before the derivative rules. See, section 2.7 was, you're still working with the definition of the derivative, the limit definition, and so problems from section 2.7, you have to solve those problems that way. So like on your next exam, if you see a section 2.7 problem and there's a number above the problem that tells you what section it comes from, you have to use the methods in that section. So some people lost some points on the exam because they were using derivative rules for the first exam, some of those derivative problems, and you hadn't learned the derivative rules yet for those sections. So, and we did talk about this, right? So I look at your work. I look carefully at your work. I got to make sure you understand the concepts. So, all right. Any questions on this problem before we move to the next one? Okay. All right. Here's an interesting function. Let me give you a moment to copy that down. Okay, so we want to find the derivative of the function sine cubed of 9x plus 1. Sine cubed of 9x plus 1. So for this problem here, how many functions are there in this problem that we? That's right, Lynn. There are actually 3. Well, you know, Zoe, let me show you. Let me show you. This here, this function can be thought of as a sine of 9x plus 1 raised to the 3rd power. So you have 3 functions here. You have the sine. Okay, you have 9x plus 1, and you have the cube. 3 functions. So it looks here like we're going to need to come up with a chain rule formula for the derivative of H composition F composition G of X. So the chain rule that you learned when you had 2 functions, F and G, there were 2 links in the chain. For this problem, how many links are going to have to be in the chain? Going to have to be 3. That's right. They're going to have to be 3. 3 links in the chain. Okay, 3 links in the chain. And so we have 1 link, 2nd link, and a 3rd link. Okay. So what's going to go here in the first the first link? Well, I guess, I mean, you know, I could write out the formula, but I'll tell you what, let's just apply the problem. You know there are 3 functions, so there has to be 3 links in the problem. So let's just apply the what we know. Sometimes we can get bogged down in notation. We've already established that y is equal to the sine of 9x plus 1, that function cubed. We've already established that. And so we're going to take the derivative. We're going to take the derivative with respect to x. So what's the outermost function? What's the outermost function? If you think of it like this, okay, I got it. If you were to do the composition, in this case, it's the composition of 3 functions, what's h of x going to be? It's on the outside, so it's got to be the outermost function. So for this function here, what's the outermost function going to be? That's good. That's right, Nicholas. X cubed. What's the next outermost function going to be? Good. It's going to be the sine of x. And then finally, the inner function is going to be that's right. Very good, everybody. Lynn, Zoe, Batsua, Nicholas. Very good. It'll be 9x plus 1. So then, when compute the derivative, you have 3 links to the chain. This is the first link. Here's the second link. Here's the third link. How many find it helpful to identify? I mean, like, how many find this, like this little step here, it's helpful? How many find it helpful? And then, okay, good, good, good. I was about that. I don't like to get bogged down in the weeds, but, you know, I'm and of course, what you see here, yeah, what you see here really is this is h prime. This first term in the chain rule, h prime. It's the derivative of f of g of x. The second term is f prime of g of x. And the last term is just g prime of x. 3 links in the chain. 3 links in the chain. We are, Nicholas. We're links in the chain for sure. We're all links in the chain, but you want to make your link as strong as possible, right? And so really what you did doing your, I mean, I could write down the formal formula for the chain rule when you have, you know, 3 functions. But intuitively, you knew it, and you know, and how many find it helpful that I wrote below here these little just the h prime of fg of x, f prime of g of x, and g prime of x. Okay, good, Nicholas, good. And then here's your final answer. That's what y prime is. All right, are there any questions at all?